Hello everyone, I am Alaul presenting our CHI 2022 paper in which we studied sleep visualizations for fitness trackers in the form of smartwatches and fitness bands. Analyzing sleep-related data is an increasingly important part of recent movements to monitor personal health. Our work was motivated by two previous studies. In the first, we found that 85% of smartwatches could show sleep data, but only 15% of wearers actually saw it directly on their watch face. In the second, 40% of the participants we interviewed wished to see detailed sleep data directly on their fitness trackers, but currently this data was not provided by the trackers. As a first step towards recommendations for sleep data visualizations on fitness trackers, we investigated which type of sleep data people collect and use as well as the types of visualizations they would prefer. We designed an online survey and collected 108 participants' responses. In the survey, we asked participants what kind of sleep data they would like to see directly on the tracker from the categories sleep duration, sleep phases, sleep schedule, sleep quality, and sleep metadata. We found that wearers wanted to see sleep data on their trackers, specifically weekly sleep duration and daily sleep phase data. We also asked our survey participants which visualizations they prefer for sleep duration and sleep phases from different choices. The visualization choices were inspired by common commercial fitness trackers and smartphone apps. We found the area and floating bar chart were the most preferred visualizations for weekly sleep durations. And for daily sleep phases, participants preferred the vertical bar chart and hypnogram the most. The survey results also showed that the most preferred visualizations were similar for smaller and larger displays, even though the fitness band size display is roughly half the smartwatch sized display. So in the next step, we wanted to investigate if scaling down the size of the visualizations affects readability or if we can safely use the same representations on the two different form factors. We wanted to measure the accuracy and the time taken to read the sleep data visualization by testing three visualization sizes, square, wide, and tall, for 3 tasks. In total, we conducted 3 experiments. We looked at weekly sleep duration first, using the most preferred visualization, the floating bars. We compared these V's for different form factors in an in-person study as well as an online study with the same stimuli to see if results were consistent. Then we tested nightly sleep phase data using hypnogram visualization for different form factors as an online study. In each study, we tested 2 types of tasks. One elementary task that requires bar comparison in the weekly sleep duration study showed in the left example image, or counting the bar peaks in the hypnogram displayed in the right example image. And 2 synoptic tasks for all studies. Answering these tasks was a bit more difficult and required an overview of the whole data. One synoptic task from the sleep duration studies is shown in the left image, and one task from the last night's sleep phase study is shown in the right image. In all 3 studies, we compared 3 specific tasks with 3 specific set of visualizations. We decided to use the floating bar chart for weekly sleep duration for both the in-person pilot and online study. It is a common visualization technique for weekly data and encodes additional information, including schedule and consistency. For sleep phases, we picked the hypnogram because of the strong preference by the participants for the fitness band. It is a relatively complex, visually busy temporal chart, and we were skeptical about how well it would perform in practice. A hypnogram represents the stages of sleep as a function of time. The purpose of a hypnogram is to provide a general sense of nightly sleep behaviors. Our initial hypothesis was that square and wide visualizations will be read more accurately and quicker than tall visualizations due to their increased horizontal size for showing differences in the bar length direction. Results: We found visualizations on fitness bands can be effectively read for different tasks, even though they display a lot of data. The negative effect of the horizontal compression seemed to be less important than we thought. We didn't find important differences between the smaller and the larger visualizations for most tasks. The tall designs for weekly sleep duration and nightly sleep phases should be preferred for wristbands in most cases because people are effective with them and wearers don't have to rotate their arms. However, tall designs didn't work for one of the synoptic tasks with the hypnogram where participants had to count specific sleep stage transitions. We saw that participants needed the longest to answer, showed in the completion time analysis on the top right, made the most errors, displayed in the accuracy analysis on the bottom right, and were the least confident compared to the other form factors. We also found that horizontal bars effectively communicate weekly sleep durations and can be safely used. Participants were confident, correct, and fast in all tasks. During the COVID pandemic, we changed our initial study design from an in-person one to a crowdsourced one, where we simulated smartwatch and fitness band screens on mobile phones. This worked quite well in general, and trends and evidence of differences across conditions were for the most part similar. Of course, we cannot perform all types of fitness tracker studies online by using smartphones, for example those that require actually wearing the device. Nevertheless, for our perception type experiments, simulating smartwatches and fitness tracker screens on a smartphone seemed to work well. In summary, we investigated how to visualize sleep data on smartwatches and fitness bands through a survey and 3 studies. We found that people could effectively rate even complex sleep visualizations on fitness trackers. In addition, we provide methodological reflections and recommendations for setting up a crowdsourced fitness tracker studies. Our work opens new questions for future research, such as how to conduct a systematic comparison of how in-person and crowdsourced study results differ for wearable devices, and test the generalizability of our findings to other types of small-scale data representations, for example the area chart, which participants also often preferred. For more information, please visit our website.